Our next speaker is Minyoung Lee, who's going to tell us about H1 envelopes and their link to the formation and evolution of GMCs.
Hello, everyone. Today I will be presenting a study on H1 envelopes surrounding molecular clouds, the work that has been done mainly in collaboration with the Alpha H1 team. As nicely reviewed by Naomi yesterday, the essence of galaxy evolution lies at the processes of baryonic cycle. Among these processes, the transition from atomic hydrogen to molecular hydrogen has been considered as a major bottleneck requiring in-depth studies. To examine fundamental principles of the H1 to H2 transition, we have been focusing on Perseus, shown here in 2-mass AB image with zero contours. As a nearby low-mass molecular cloud, Perseus harbors several dark and star-forming regions, which are indicated in blue and red respectively. One of the major findings in our 2012 study was that the H1 surface density is remarkably uniform, as illustrated here for B1 East, one of the dark regions in Perseus. In this plot of H1 surface density as a function of H1 plus H2 surface density, we calculated the y-axis values using Alpha H1 data under the assumption of optically thin H1. For H2 surface density, we used IRA 60 and 100 micron data and derived dust column density. And the dust column density was then divided by a local dust gas ratio. And then H1 column density was subtracted to estimate the H2 column density. This dust-based method has been frequently used both in galactic and extragalactic studies. And finally, all finite pixels at 0.4 parsec resolution were used for our analysis. As I mentioned, we found that the H1 surface density has an incredibly narrow range of 6 to 8 solar-mass per square parsec. So this H1 saturation is consistent with predictions from steady-state H2 formation models, such as Krumholz 2009 and Sternberg 2014. In these models, H2 forms in the regions where 5B photons are sufficiently attenuated by dust in the H1 shielding layer. In solar metallist environment, this H1 shielding layer has a characteristic column density of 10 solar mass per square parsec. You will hear more about these models from Elijah's talk later this afternoon. On the other hand, this H1 saturation could result from simply a large amount of optically thick H1. So while H1 envelopes surrounding molecular clouds have been frequently noted in both galactic and extragalactic observations, many of their characteristics remain unknown. In particular, we are interested in the following questions. First of all, what are the properties of H1 in and around the molecular clouds? How different are they from those of H1 in the general ISM? Are the H1 envelopes indeed shielding layers for H2? And finally, is there any link between the properties of H1 envelopes and the evolution of molecular clouds? Our approach to address these questions is to perform comprehensive studies of H1 in absorption toward Perseus and other molecular clouds. As a pilot study, we obtained H1 absorption measurement toward 26 continuum sources behind Perseus using the Arecibo telescope. In this column density image with zero contours, the sources are shown as the red crosses. In essence, H1 in absorption is measured by performing on and off observations, producing an emission spectrum coming from both the CNM and WNM, and the absorption spectrum mainly coming from the CNM. Following Heiles Troland famous Millennium Survey, we then performed Gaussian decomposition of these emission and absorption spectra, deriving the peak optical depth, spin temperature, and H1 column density of 107 individual H1 components. Based on this Gaussian decomposition result, we then compared the properties of individual H1 component in Perseus with those for the general ISM presented by the result from the Millennium Survey. Our Millennium data are in green and black. First, we found that our median peak optical depth is about 0.2, and only handful number of components have the peak optical depth higher than 1. With comparable sensitivity shown as the green dotted line here, our study agrees with the Millennium Survey. Next, we found that our spin temperature has a median of 50 Kelvin and agrees well with the Millennium Survey. Similarly, our CNM and WNM column density distributions are comparable to those from the Millennium Survey. In summary, we found that all properties of individual H1 components in Perseus are in good agreement with those from the Millennium Survey, suggesting that individual H1 components are similar between a smaller field around the molecular cloud and the random general ISM field. On the other hand, we found somewhat different results regarding integrated properties. Here, the line of sight integrated CNM, WNM, CNM plus WNM column density, and CNM fraction in our study are shown in green. The same properties from the Millennium Survey are in black. The main conclusion from these plots is that the integrated properties in our study trace mainly the upper part of the Millennium histograms. Specifically, our median CNM column density and the WNM column densities are more than 5 times higher than the corresponding median values in the Millennium Survey. Similarly, the CNM fraction in our study has a median of 0.3, which is slightly higher than what Heiles Troland found. Considering that two studies have comparable sensitivities, the discrepancy we found most likely result from intrinsic properties of the Perseus region. Our result suggests that the H1 envelope of Perseus has a higher total H1 column density and a higher CNM fraction compared to an average random ISM field. Next, we examine the impact of cold H1 on the H1 envelope by finding an empirical relation between H1 column density calculated under the optically thin assumption and the correction factor. This correction factor for high optical depth H1 is defined as a ratio of the CNM plus WNM column density to the optically thin H1 column density. We calculated both quantities for each of our 26 sources using the Gaussian decomposition result and fitted a linear function deriving the following empirical relationship. This relation was then applied to the optically thin H1 column density from Liera 2012, allowing us to compute the correction factor on a pixel by pixel basis. The maximum correction factor is only 1.2, suggesting that optically thick H1 is not substantial in Perseus. The H1 column density was corrected accordingly on a pixel by pixel basis, and this opacity-corrected H1 column density was then used. We derived the H2 column density. The H1 and H2 column densities before and after the correction are compared here. The similar histogram suggests that the opacity correction is indeed minor. Specifically, the correction increases the total H1 mass by only 10%. As a result, H1 surface density versus H1 plus H2 surface density for the individual dark and star-forming regions in Perseus rarely change. This is the plot before the correction, and this is after the correction. And the H1 surface density still saturates to 7 to 9 solar mass per square parsec, and this is again consistent with H2 formation model prediction, where characteristic surface density of 10 solar mass per square parsec is predicted for the H1 shielding layer in solar metallic environment. So I finished my talk with a summary and future work. First of all, based on the Arecibo H1 absorption measurement, we found that the individual H1 components have similar properties between a small area around Perseus and the general random ISM field. On the other hand, the H1 envelope of Perseus has a higher total H1 column density and a higher CNM fraction. We also show that the correction for high optical depth is minor, and the opacity-corrected H1 surface density is still uniform with the 7 to 9 solar mass per square parsec, suggesting that H2 formation is mainly responsible for this H1 saturation on 0.4 parsec scale. As for the future work, we are currently in the process of doing similar analysis for other galactic molecular clouds. For example, we have recently extended our H1 absorption measurement to Taurus, Rosette, Orion, and Ophiuchus, beating the Millennium Survey in terms of the number of sources. So our comprehensive studies of H1 envelopes around the molecular cloud will be in particular invaluable for the coming ASKAP era, where a large number of H1 emission absorption measurement will be available for us to build a comprehensive picture for phase transitions in galaxies. Thank you very much for your attention.
Okay, questions. Let's start with you. Yes.
Okay, I have just a comment and a simple question. Actually, you used 60 micron and 100 micron iris data in deriving the H1.
Yes.
But actually...
no, to derive H2.
Yes, yeah. Including H2. Yeah. But actually, it is in the Wiens regime of the Planck distribution. So you do not have enough sensitivity to really measure the dust optical depth. So I would recommend you to use some millimeter data, for instance, taken by Planck. Then you will get a fairly different conversion factor of the dust emission into the any kind of hydrogen. And yes. The other question is, although you didn't mention about XTO factor, but according to your paper, XTO factor is quite small compared to that typically discussed XTO factor. Do you have any comment on that?
Yes, about the H2. Yeah, so I agree that the Planck is better. You know, it has better sensitivity and it's more sensitive to the high column density regime. You know, my thesis was done before Planck, so I have excuse, in fact. But Elijah, Yes, Elijah, my colleague, he's actually working on the same thing using Planck data, and then yes, I do agree that H2 in my study, older study, could be underestimated for high column density regime. But what I want to emphasize is that all this result is about H1. So it's not affected by underestimation of H2 column density. And then your second point about what was the XCO, yes. And actually, I think Isabel will be talking about her gamma ray analysis of the same region, actually getting the same result, which is very interesting. So yeah, I leave the answer to her, maybe this afternoon. Yeah.
Question by Chris while the next speaker sets up.
Yes, I have a question about some of the numbers that you gave. You mentioned that the median optical depth was 0.2.
Yes.
but the increase in the mass was only 10%, so I don't understand that. And the second thing is that you had a very broad distribution of optical depths, and that would mean that the mean would be larger than the median, and so it'd be more than 0.2, and then that you should actually use the mean in calculating the total H1 mass. So could you explain that?
Yeah, so the way we calculated a correction, the way we applied a correction is actually from the integrated properties. So we calculated a correction factor based on the integrated CNM and WNM column density. So it's not really, so the number 0.2 is actually for the individual H1 component. Does it really answer to your question?
But then what about the fact that the mean would be larger than the median?
The mean.
When you have a large range of parameters, then the mean is generally larger, dominated by the largest items, just as Yasuo mentioned in his talk.
Yes, I agree that given the distribution, the median values could be different, but again, the correction was done using the integrated column densities, you know, the integrate along the whole line of sight. So it doesn't really depend on the median.
Yeah, we can talk later.
Yeah.
Okay, let's thank Min Young again.